Hello everyone. In this lecture, we'll talk about text processing. So how do we process a text before we start modeling the language of the text or use the text for the different downstream applications, NLP applications. So there is a very fixed few steps which comes very beginning of this NLP system pipeline, and we'll discuss about them in this lecture. So you can think about text processing as a extraction and cleaning of the text before using it. So very first thing comes here is that how to convert the natural language document into a computer readable format, because many of the documents come as a PDF or a Word document, or sometimes from the portal we extract the information that would be in form of HTML. So all these formats are kind of normalized to a linear plain text with the coding like ASCII or UTF-8. And this is very important. So after extracting the document into the linear plain text format, then come to the part of the text normalization. Why this is very important? Because a word can be presented in the document in very different form due to the use of singular or plural or usage of tense, or many cases we use those few things to make the same word as adjective and the noun as well. So we have to find out all those details before we start processing with them. And here I really want to mention that this particular normalization process, or this processing what we're talking about while we clean the text, it's very, very language specific. Different language has different characteristics. And because of that, we have to handle the language or the text differently. We cannot use the same rules or methods for every kind of text. So before talking about the processing pipeline, let's first discuss what is a corpora. As I have just mentioned, that all this language model or the system built upon some data, and we must know, or this data must come from some place, and that's exactly is the corpora. So it's a machine readable collection of data, either in form of text or speech. In NLP, often it is work also with speech to text translation. So there are speech corpora as well. So when we look at one single corpus, we then take the corpus, then process the corpus, and then build the language model or use the corpus for the downstream task. Now, before we move forward, let me talk about a few more things regarding corpora. As I just mentioned earlier, that many of these text processing tasks actually language specific. And that's why it's very important for us to know that what are the language of the corpora. So we call them a dimension of the corpora. There are many different dimensions, and there are three most important dimensions, which will be talking about here. So the very first one is the language. It's not about only different language. It is important to know about the dialects of the language as well, because with the dialects, many grammatical rule, semantic meaning changes. The second very important dimension is genre of the text. You can think about it's a more general category of the text or the lingo of the text. So if you look at this research paper, the language we are normally use to write these articles are very straightforward, using active tense, and also we write a very precise sentence, not a very lengthy sentence. So the information we transfer through this research article get very precise. On the other hand, if you talk about a fictional book, science fiction book, or if you're talking about any fiction, non-fiction book, or any kind of literature, the language become more verbose. So, for example, on the other hand, if we look at the Wikipedia article, they're talking about more active voice like research article, but the sentence length is much longer. On the other hand, in this fictional, we often use many passive voice as well. And last one, which comes here in the dimension, is the time. With the time, language change as well, right? It's not about genre. The same fiction with similar kind or similar genre of fiction, which has been written in an 1800, use very different language than things which is currently being written, right? So time also very important. For example, if you look at the message, like Twitter message, there are cases when you write Telegram where you have a limited number of words to fit in, but we do not use the words or the language we use when we write the Twitter message or Facebook message or Instagram messages. Here, not only that we are not really strict about the language syntax, we often use a new word which does not exist in the English language dictionary. And even though it is not existed in the dictionary, the word become a part of the language. For example, here, ya become a term, a word, which is, if you consider separately, will not give you any valid meaning. So it is very important before we start the text processing to know about what are these dimensions, and based on that, you will design your processing pipeline. So let's talk about first part or the very first step in this pipeline, that is tokenization. So what does this mean? It's nothing but splitting a whole file of text file into tokens. What are the tokens? We will not use the word term word, but rather we'll use the token. So it's exactly the word form, which is written in the file. Let's say file is a full string, right? It's not a separate we don't have string for every word. And exactly that is what we're doing by the tokenization. We are creating the string that exactly mean one single word form. And that's we call the token. So before moving forward, how do we do the tokenization? Let me give you two small definition as well. One is the type. Type actually is a class of all tokens that have the same character sequence. So for example, here, this token and this token, the third position from the left, the token, and the third position token from the right are the same token, same type, but two different tokens because it appeared in two different positions in the text. So when talk about token, the position matters. When you talk about type, it's just considering the string of character. So if you look at the total number of tokens here present is 11, but the number of types we have here is 10. Now, in addition to that, there is another definition I want to introduce here, that is term. And term is actually you can think about the type which actually included in the dictionary. What is the slight difference between type and terms? Because you can include each type from your file to the dictionary, but you can also do certain normalization, which we'll talk about later, and find the root word or possible shortened word. And that particular word form, with the normalized word form, that we're going to use as term. And often, actually, after doing normalization of types, we convert the type to the term, and those normalized types actually put into the dictionary and work further with those terms. So in this particular case, you can think of that in this, so if the puzzle and there is something earlier was like puzzles, then this S is removed, and then this word and this word, this become a type, or on the other hand, you can say this is actually the term I would like to introduce in the dictionary. So now coming to the part that what are the basic tokenization process. So here what you can see, what I have done is simply remove the punctuation. All the punctuation I have removed. And then I split the sentence or the string based on the blank space. It worked perfectly for this scenario. But there are many other scenarios where this basic method can provide some wrong information. For example, if this is an auto, this information, every sentence or this thing, who in the world am I, written in one particular line, and the next line written, that's the great puzzle. In that case, this blank space would be removed or replaced by /n. In that case, if I do not use /n also to check for the gap or the where one particular word ends and another term starts or token starts, then I'll be wrong. So it's not only the space, maybe we need to look at the tabulators and the new line characters as well. But even with that, we can have many problems. For example, if we remove the word apostrophe here from the word boys, this is kind of acceptable. However, if we remove the word here and we remove the space as well, because the same manner, then we'll reach the word can't, which is a different meaning. On the other hand, even if we use removing the space, keep the space here and remove the apostrophe, we'll have can and t. None of this actually providing lots of information or the similar information like can't. So when there is a short form used, then this apostrophe cannot be considered just removing the apostrophe or replacing the apostrophe with blank space. We have to do more. On the other hand, if you look here, we often say that we'll remove all the punctuation, but here or this special character, if we remove those special character here, then these are completely different meaning. It will not mean the domain name here. The support will be the complete different word or the token here, nothing to do with the eb.com. So there are those problems definitely exist if we do with the tokenization method. Another very, very important problem here is the white space. There are many words that span actually over multiple tokens, like Los Angeles, white space. White and space are two very different words. And if you actually bring them together, then they have a very different meaning. So in this case, removing this particular space would lead to a problem. There are many languages like German, Sanskrit, where we combine multiple words together to make a longer words. Like here, Leben is one word, Verschischerung is one word, Slapt is one word, Angstelle is another word. And the four words has been combined into one single word. So in this case, there is no space. So I cannot actually divide this particular word or this token according to my basic tokenization method. I have to use a different method here. I have to find the longest string or the smallest string match with the dictionary, and that comes to an end with S. So those things are important. I wanted to mention this example to emphasize that how important to know that what language you are using before tokenization, what kind of words or what are your intent, whether you are looking at the entity as well to form as a word, or you just wanted to get all the token. Those things are important, and accordingly, you will find a tokenization method that will work best for your purpose. So moving further, there are many cases where sentence segmentation is also required with the tokenization. So for example, if you consider, remember what we talk about lexical semantic, then on one level up, there is compositional semantics, when multiple words together make a certain sense, right? So multiple words together also in a sentence. I gave one example in the previous lecture. The sentence need to be also have certain meaning, and those are important things also to understand. And for that, certain cases, the sentence segmentation is also required. Especially when we are using this, we talk about the LLM, this large language model, sentence segmentation is an important part. So in this particular case, if you look at this example, what we want is 3 sentences. But if we just pause or cut the sentence based on full stop, what you will get, this is the first sentence, till doctor is the second sentence. Then the third sentence is actually one single token. Then again, this is another sentence, and then the last sentence. Now, definitely using dot will not work here. On the other hand, if you just use that, you have to use dot, and you have to see whether the next word is a capital letter or not. This part you can actually do it properly. However, here you will not able to correctly identify. And this is because there are some abbreviation has been used, and we have to understand this abbreviation. They are also using dot. So we have to look what are all the scenarios where dot can be used, and from them, what are exactly the cases where dot is used for the separating 2 sentences. In this particular case, actually, we can think of formulate this problem as a decision tree problem. So every label, we ask a question and we find out whether it's a yes or no, and based on this outcome, whether the sentence satisfies that condition or not, we'll further move on the tree. So very first thing, we look at that lots of blank lines after the word, then definitely it's end of sentence. If there is a punctuation like exclamatory mark or question, definitely that's sometimes end of sentence, because we do not use those punctuation in between, like not like dot. But it depends, right? If there are different kind of corpora you can have, where you have different punctuation for mentioning the sentence ending as well. So this is a basic structure here I'm posing here. So moving forward, now come to the next part, that is the stop words. So what is a stop word? These are the frequent word that does not carry much information about the content we are sharing. It's mainly used to create the sentence structure. So often we call them as a function word. And these words are often used because every sentence uses them to form the structure. So it's often used repeatedly in the corpus. And these things these terms we often actually omit. We can specifically create a list with stop words or the words which want to remove, or we can actually implicitly build the list by just taking top k most frequent word. Why sometimes explicit list is important? For example, if you're using a very specific domain topics to talk about or a text, and if you do have a certain particular word appearing multiple times because we're avoiding using pronoun for that particular word, then that will become also a very redundant word in the text. But you might not be willing to actually remove the text from remove that particular terms from the text. So in some cases we can use the fixed list. So mostly, as I just mentioned, these are the function words in the large corpus, and the main motive to removing them is to save a significant space. However, some cases it also causes various problems, like if you take this particular first phrase to be or not to be, if you start removing the stop words be or, then it's just like two or not two, which doesn't make much sense. Same as with or without you. Even though this is actually a song name, we should not actually remove anything from there. Or the who, if I remove the, this become only who, and who is a very different idea from the who, which is actually a character. So it's very, there are a few cases where we still remove stop words, but more trends coming, like when we will not remove them completely, or we'll keep a very short stop word list, because we have seen that removing them does not, though even it saves some space, but it does not really contribute a lot to the effectiveness of the NLP models. The third in the processing is the stemming. What is stemming? We said that the word present in a very different forms, right? Due to the singularity, plurality, or the tense. And our adverbial forms, different things. So stemming actually cut the word very crudely, and that's why often the word after the cutting the end part of it does not really give us a very a word in the language, but definitely it's a unique term to be presented in the dictionary. And one thing I really want to mention here, if we are using stemming or any of this process, particularly in the context of information retrieval, you must operate all this process on also on the test data, because otherwise your vocabulary or your dictionary words will be very different from the training data and the test data, or the word, the corpus we have used to build the system, and later when the user interacts with the system. So here, we in English, we often use Porter stemmer. It's a very popular stemmer to get rid of the different word forms or find the root word form. And it worked pretty well with the English, because English is not morphologically that rich, but the morphologically rich languages, in many Asian languages, stemming performs actually stemming has a very adversarial effect, and we do not use stemming. So here is an example. This particular sentence, if you use the Porter stemmer, it will become this particular case. So you can see that here Y is replaced with I, or here E is deleted. So those are the things the Porter stemmer does. There are very fixed handwritten rules for them. The another way to deal with this different word form, to normalize them to a single a root word, is called lemmatization. So here we do a full morphological analysis of the word, and based on that analysis, we try to find what is the root word and how that word form, which we are looking at the token, which is presented by the token, is actually we can come up with. So here, saw can be the root form see as var, and then the past tense. On the other hand, it can be a word, root word saw with the noun. Both can happen. happen. And that we can only able to do with the morphological analysis. If we use stemming, it will be either lead to S or saw. Now this does not have any meaning at all, right? So how do we do it? Basically, what we can call say that it's a consists of stem and affixes. So one is the stem is the root thing or main content, and the affixes help to get it a bit different form. For example, here we are using a affix within the word, and it is called infix to make the runner up to runners up. Here we are actually using actually one prefix and one suffix as well. Here we are only using prefix to make happy to unhappy. It's changing also the meaning. So it can change the meaning, it changes the form, many usage is there. So when we do the morphological analysis, basically we find the morphemes. So rather we have a word, we have a dictionary of morphemes. That's the smallest meaningful units. And every word can be presented as a combination of multiple morphemes. So stem, affix, both are actually morphemes. Unhappy has two morphemes. One is un, which represent the negativity, and the happy is the has already a meaning. And from here we can see that there are two different kind of morphemes we have. One is free, that can have their own meaning like happy, and bound morphemes that have a meaning but we do not use it when we wanted to really represent the meaning itself, but we present it or combine it with another morpheme to present a new word form for from a root word or root from a stem, and then it can give a new meaning to it, and that is the bound morphemes. So un, ill, in, all these are bounded morphemes. Here, another thing is important to say, how do we actually do this analysis? So what we do, we create the finite state automata which see that what are the morphemes that can be actually combined together to create a new word in the language. For example, I should have a finite state automata saying that ill and happy cannot be merged to make a new word form. However, ill and literature can be combined together to make a new word form. So that's how you see how the word can be acceptable. On the other hand, we use finite state transduction to find how a particular word or a particular word form actually changed from the root form. So from saw, I mapped it to the C verb plus past tense. Now, there are other processing ideas we also have, or other processing we do as well. Often, if there's a diacritics, we remove the diacritics, or we find certain normalized string set of string to replace the diacritics. Like u umlaut can be presented always with ue. Here you can here we remove these and we present just by u. This is a better, comparatively better approach. On the other hand, you can have the lower and upper casing, and definitely it leads to some information decay as well. For example, if this is United States, the United States I'm talking about, and we do the lower casing, then definitely it's a completely different meaning now presenting, right? It's just certain states being united. There are cases when we talk about particularly Asian language, then often characters already have their meaning. The engrams, the two sequence of character can hold the meaning. And there we really do not go with the blank space tokenization. Rather, we go with the character by character tokenization. So particularly, this is used in the Chinese language. And lastly, in the pipeline is the spelling correction. So user may not know the spelling, there could be a typing error, or there could be the error due to some translation. So all of these must be handled. We should not just discard the word because it doesn't match with any terms in the dictionary. So what we do, we actually map it to the closest term in the dictionary and include or consider them as that dictionary term. So there we require a notion of distance to represent the which is the closest. And how do we define this notion? We can think about that the distance would be there if a new word is introduced, like here, it's supposed to be house, but the O is introduced here. Or here O has been deleted. Or here O is mislaid and replaced by a wrong character. Or there are cases which is as heard spelling, like they phonetically they are same. We can also use them, particularly when we do the speech to text translation. So here I'll talking about or introduce one particular distance method which is very frequently used in the text processing, Levenshtein edit distance. It defines by the minimal number of edit operation we require to change a string X to Y. Now, why I say the minimal number of edit operation? Look at this earlier example, whose versus house, right? Here, one thing is that I just delete this O and I can transfer this word to this. Or what I can do, from this, I actually change this to U. U is changed to S. S is changed to E. And finally, this is deleted. So if this is the case, then my distance would be 1, 2, 3, 4 operation, so 4. Now, definitely we would not like to find this as a closest distance. I will consider this one as the closest distance. So we can actually change one string to another by various operation. We'll consider only the minimal operation. And this, because we are using that, we actually use a dynamic programming by transforming prefix substring. So I'll talk about this actually with the example. So what I'm actually saying that to understand or to know that how many minimal operation is required to change C to K, I need to know how many operation is required to this previous string to this previous string, that is the first one, or how many operation is required from this one, which means how can I transfer C to null, that is the one string, and from here I can calculate, I can change C to K. Or if I have this information that what is the number of operations required from coming null to K, I can use this particular information to find this particular, the minimal number of operations were required. So if I consider that, the very first thing, as you see, this null to null, if you consider diagonally, actually it is coming from null to null. And here, if I can simply replace the word, my cost would be 1, right? On the other hand, if I already coming from this side, from the top, that means what information I have here, that what is the possible for possibility or the cost, minimal cost for transferring null to K, that is with the 1 insertion. And now if I want to change C to K, what I have to do, I have to delete the C. So that is exactly coming from this particular equation. And lastly, if I come from this direction, then what information I have, that what is the cost to change C to null. So if we change C to K, what I have to find from this null, I have to come to the K. So 1 additional insertion, which is this one. So for both cases, it would be 1 plus 1 this would be 1 plus 1 if I come from the top side, and this would be 0 plus 1. So these three are the cost currently I have here, and definitely I will choose the minimum cost. And we'll proceed after that here. So now I have information, diagonal information, information from up, information from side, and I'm already very good to get to this information. So the C is not equals to A, so if I have to replace, I have to add 1 here. If I'm coming from the top, again, C I have to delete, so I have to add 1 here and here as well. So the cost would be 3, 2, and 2. And minimum would be any of these two costs. So if we continue all the filling about the cell, this is the cell which will give me what is the minimum cost to transfer this full sequence, the whole I sequence to all the J. So here we can track back as well, that how will come from null like cat to get. That is also possible. So one thing I just wanted to mention, it is possible that one single word form which appears like a token in the text can map to multiple word terms in the dictionary because they have both similar distance or minimal edit distance here, MED. Because here, if you just insert A, this is the only one single operation required. And here I have to replace E to U. That is also one single operation. So with that, I would like to say that there is possibility that to map this to multiple units, but then there is a context which you need to use to find actual what exactly it's a meaning or meaning of the word with the context. If it's a bright, the previous word is bright, then maybe it's the future. If previous word is sharp, then maybe it's the future. So overall, in this particular lecture, we looked at the basic pre-processing pipeline or the text processing pipeline. And we start with the tokenization, some cases sentence segmentation is required. And then we'll go with the stemming or lemmatization, stop word removal, and finally the spelling correction. And what is very, very important, as I said, mentioned many times, what are the steps you are going to take, these pre-processing steps we're going to take to normalize your text? It's very much depend on the application and the language you use. Thank you.